Hello. In this video, we're going to look at some systems of equations that involve two variables, but the equations do not represent lines. So some nonlinear systems of equations. What we learned about linear systems of equations still applies. The algebra just gets a little trickier, and graphically, it's a little more complicated than just finding the intersections of two lines. So we have more possibilities of possible intersections. So, for example, we could have more than one answer if these things hit twice. And in fact, in this case, this is what we're going to have, because just a rough idea of the shapes here, I have y equals x minus 1. Well, that is a line, and I know that that line looks something like this. And this other one is actually a curve. I'm not entirely sure exactly where it's found, but it's something along these lines. So that curve can have two intersections. It's still possible to have no intersections. It's possible to have only one intersection. But what we're looking at is something that's kind of going to look roughly like this. On a graphing calculator, you could graph it and find intersections. But if I have to solve it algebraically, I can use many of the same techniques that I've used before. So I'm going to use substitution here because y is isolated, so that's relatively straightforward. So if y equals x minus 1, but y also equals x squared plus 3x minus 16, then x minus 1 must equal x squared plus 3x minus 16, because as we know, y equals y, and both of these things are equivalent to y. So what I now have is a quadratic equation. So I'm going to bring everything over to one side of the equation so that in this case, the left-hand side is 0. So I'm subtracting x from both sides. So this becomes x squared plus 2x. And I'm adding 1 to both sides, so minus 15. This is now a factorable quadratic. So to express this as factors, the factors are going to be x plus 5 and x minus 3. Which means that in order for this product to equal 0, either one of the two factors has to equal 0. So either x equals negative 5, which would make x plus 5 equal 0, or x equals 3, which would make x minus 3 equal 0. Well, if x equals negative 5, then I can substitute that value into either one of the original two equations, and I should get the same y value. Obviously, the easier one is to subtract 1. So y equals x minus 5, x minus 1, so negative 5 minus 1 is negative 6. But if I did substitute in, negative 5 squared is 25, plus 3 times negative 5, which is negative 15, so 25 minus 15 is 10. And then 10 minus 16, I've got my minus 6. In the other instance, if x equals 3, y equals 3 minus 1, so 2. Again, substituting 3 into the quadratic equation would also give me that same y value. This means that the coordinates of the two intersection points are negative 5, negative 6, and 3, 2, which does roughly match sort of what I've drawn in my sketch up there, even though it wasn't perfect. So those are two intersections that represent the solutions to this system of nonlinear equations. Here's another example, and again, we can do a substitution. The first equation is exactly the same, the y equals x minus 1. The second one is a little more complicated. So we have something that isn't, the y isn't isolated, but I can still do a substitution. I can turn this into x squared plus, I replace the y with x minus 1. So now instead of y squared, I have x minus 1 squared equals 25. If you're interested, the y equals x minus 1 is a line. The x squared plus y squared equals 25 is actually a circle. So again, I'm expecting here to see two intersections. But again, it would be possible not to have any intersections, for example, if the circle was over here and never intersected with the line. In this case, we will find some intersections. So again, a quadratic equation. So I'm going to distribute everything and bring it over to the same side of the equation. So x squared plus x squared minus 2x plus 1 is what I get when I expand out that squared binomial. And I'm actually going to subtract 25 from both sides. So I have minus 25 so that I have equals 0. This then becomes 2x squared minus 2x minus 24 equals 0, which I can actually now divide both sides of the equation entirely by 2. So I get x squared minus x minus 12 equals 0. Again, we have a factorable quadratic. So the factors are x minus 4 and x plus 3, which means that since that product equals 0, either x has to equal 4 or x equals negative 3. And again, based on those x values, I can calculate the y values. Definitely using the first equation, going to be much, much easier. y equals x minus 1. So if x equals 4, y equals 3. And if x equals negative 3, y equals negative 4. I can verify that these work in the second equation because 4 squared plus 3 squared is in fact 25. And negative 3 squared plus negative 4 squared, exactly the same sum, 25. So these two intersection points are the points 4, 3 and the point negative 3, negative 4.